Sure. Hello everyone. Today I'm going to present a paper called "Towards Better Generalization of Adaptive Gradient Method." And I'll first introduce some first order gradient optimization for deep learning. So as we all know, there are many good progresses in first order gradient optimization for solving the deep learning neural network models. One most dominant algorithm is called SGD, stochastic gradient descent. And since it performs well across many applications, and because of it's very simple. And however, there are advantages. There is an advantage of SGD, which is it scales the gradient uniformly in all directions. This may lead to poor performance as well as limited training speed when training data are sparse. So to with this case, there are many methods posted as well as some adaptive gradients that to scale the gradient by some square root of some form average of past gradients. For example, for Adam grade or something, you can see, in order to the delta theta is a gradient, here. And for example, for SGD, we can directly get gradients and times minus alpha, that is updated row. But in order to make sure the SGD better, they add more variety in this updated row. You can see for momentum, it changed the GT to MT by combine the past gradient here and the new gradient. So that's because although they are very popular, so the generalization of the adaptive method is worse than the SGD. So things like adaptive method often display fast progress in initial portion of the tree, but the performance quick reduced or reduced on the data. That's the test data or something. So and the SGD method is also shown in several recent state of art method like NLP and computer vision, which is a good choices. Things like this in this applications, SGD performs better than adaptive method. So although some papers try to solve this kind of general problem for SGD, but for the adaptive gradient method, so their analysis still have some gaps and fail to explore the critical generalization capacity. So in this paper, they try to build a good adaptive gradient method which have better generalization. Here in this work, they consider a problem is called stochastic non-convex optimization problem, and this problem tries to approximately match the population loss after again an ID set Z1 to Zn from the Z1 to Zn from known distribution P. Here the Z is their data sample from another distribution P, and the W here is the parameters of the learning model, and L is the loss function, and the loss function F of F is the population risk, and which is non-convex because for most deep learning tasks, and because the availability of this distribution P, and there is a challenge to directly solve this population risk problem. So the papers try to solve empirical risk problem like this one based on only n samples, n Z1, Z2. And this is the empirical risk f hat w. And as I mentioned before, like the goal is try to improve the generalization performance for the adaptive method. So for like ADA great LP. Now, so like how to like measure utility for the when using this grid method. Like we find something like there are two things like like optimization bounds for training objective. That's the norm of empirical gradient, or the generalization bound is the normal population gradient. The reason we consider this because like the finding the global minimum for non-convex function here is because it's a non-convex function, so the solution global minimum is NP hard. So the utility of the model is measured by the normal of gradient. So the main idea is in this figure here. This the left part is the ideal case. The ideal case is we can access to unlimited training samples. What does mean? Because like the current adaptive gradient method only follow a typical stochastic optimization oracle or paradigm. What that means? That means like they try to use the gradient to update the parameter, stochastic gradient to update the parameters. And this kind of a stochastic optimization oracle requires a new sample every iteration to get the stochastic gradient expectation. And expectation like this because like this gradient is computed as a new samples, so which is equals to the population gradient. However, because like in practice we only have finite training holes, and so we need to reuse the optimization, reuse the number of the data's number of times, and that means like epochs, right? We train the models over epoch 1, 2, 3, many apps. Some papers found that like the generalization error increases with the number of times like the optimization will pass over the data. That means like and the generalization over is proportional to the number of epochs. So it's it is expected that like the gradient descent will much more behaved if we can access to infinite number of fresh samples, so that like the sample gradients stay close to population gradient across all iteration, and which leading to high probability bounds on the population stationary point. So in order to do this one, like we need to consider how to reuse the data samples, and that's the part of the generalization of the algorithms. So this paper, they propose a stable adaptive gradient algorithm, SAGD. And the SAGD is try to like behave similar to the ideal case of access to the unlimited training samples. Borrow the idea from the differentially private mechanism, and or different mechanism. The main idea is that like we in the algorithm, like we access the training data through a differentially private way and compute the optimization and compute the estimated gradient of the object function, and then we can use the differentially private gradient and perform a descent step with adaptive step sets. So that like after we use this one, the training set will maintain the statistical nature of the fresh data, and we can run multi-pass over train data. They prove that the reused data samples in SAGD like nearly we can access to the statistical nature of the first sample, which will get which like the sample gradient will concentrate to the population gradients across all iterations, and the normal population gradient will converge with high probability. And they also gave an upper bound for the number of iterations. Since they consider differential privacy, so I will introduce a basic idea of what is the differential privacy. So differential privacy provides a privacy standard for data privacy. It guesses that there is no much difference between the output of the algorithms over data set that differ one data element. So when we have this relation, when we have this theorem, and a random math algorithm M is called data differential privacy. If for all neighbor data set DND prime, the DND prime is neighbors. If that means if the data sample, only one data sample is different, and we have this inequality holds, and like the epsilon here is the privacy budget, delta is the probability of failure. Intuitive, like this example, like here we have two data sets, D and D prime. Only the first data sample, the person is different, and the way input to a random algorithm, we got the output MD and MD prime. The differential privacy requires the distance between these two distribution is bounded by e to the power epsilon, and there this part is some probability of failure. So there are some basic properties of differential privacy, like for any differential for epsilon DP algorithm, and B we have new function B over the output or the P algorithm is epsilon DP for the post processing of the B this function. And to achieve the differential privacy, there are three. One is to add Gaussian noise, the other one is to add Laplace noise. That means there is a query function, and we can direct add a Gaussian noise here, and it's epsilon delta dp, or the noise we choose from, the noise variance is choose from like this one, proportional to this parameter. And delta here is the sensitivity, and QD minus QD prime. D and D prime is the neighbor data set, and delta the epsilon is the epsilon delta differential privacy. And here, and we can also add a Laplace noise. That means we can add a Laplace noise. And here is query add Laplace noise, and the variance sigma is proportional to the delta divided by epsilon. And here is L1 normal activity. The basic properties of privacy. So this paper, the first problem this paper holds is SGD with a loss mechanism. So you can see in this this algorithm, the SGD algorithm needs to compute the empirical gradient G title here, and update the model parameter through the sigma PLP update the row. You can see like follow the basic row. The only difference is to how they get the empirical gradient, the G title here. So they after get the gradient over the data set, they add a noise, the Laplace noise, and to make it a different private, and then run the then we can get a noise gradient, and then we can do the optimization steps here. And they prove that like this algorithm is satisfy this kind of epsilon delta differential privacy. You can see this part is epsilon, and the probability is related to the time of the iteration number T, and the G1 is there is the sensitivity. That means the norm of gradient, and N is the number of local data set, and sigma is the variance of the N. So to analyze the convergence of this algorithm, they try, as I mentioned before, we consider L2 norm of a population gradient, right? Because we want to consider a generalization bound. So so we need to show that the empirical gradient, which is approximate to point grade with high probability. And that means error. That means this kind of error, this empirical risk, and this is a population gradient. This error is much small through the number of iterations. So in order to get this kind of information, like we need to present, we need to to first give suggestion guarantees and differential equation algorithm. So this is one. So this lemma shows that for any differential gradient descent algorithms, like which we only access the training set S with set N, and the parameter WT, you can this output parameter, and the gradient is and the GT hat here is spherical gradient, and we can see given some conditions for the zone delta and the sample size, we got this. We can get a concentration. This kind this the empirical data and this solution gradient. So what does it mean? This means that if the privacy cost epsilon is bounded by the estimation error here, and is bounded by this error here, and the different pricing mechanism can enable the reuse the train samples maintain a statistical guarantees as if they were fresh samples. That means we can achieve this concentration bound. This means the distance between the empirical gradient and the population gradient are bounded with probability. And so things we consider if we want to use this concentration bound, we have there the condition for the epsilon, and epsilon smaller than delta divided by 13. And since as we showed the SJD algorithm is satisfy epsilon delta different privacy. So after enforce this condition, we can get an upper bound for the total number iteration. This is upper bound for the number iteration. So following the result I showed for the general differential privacy algorithms, it can have that kind of generalization performance. So the gradient produced by the S3 with a Laplace mechanism maintain a high probability bound, the concentration bound, and that means the noisy gradient approximate to the population gradient, like this one. So you can see this is a concentration bound for the specific SJD algorithms, and you can see there is the concentration error and this high probability. We can have the higher noise level, the sigma here, higher level, which is the better privacy guarantee and a large number of iterations, but we have more concentration error. So there is a trade-off between the noise and the accuracy. And also you can see here for the beta and mu here. That means this the probability here. The large mu bring a larger concentration. Large mu bring a larger concentration error. Here is larger, but more probability. A larger beta will bring a larger upper bound. Upper bound for the iterate number, but also a large number of a large value for the probability. So how to optimize the values of the sigma, beta, and mu, and total number iteration, which can better to analyze the coordinates to the population stationary point, and they prove that they prove non-symptomatic coordinates rate population like this one by optimizing these kind of parameters, and they show the population gradient is smaller than in this level. What this means? That means given n samples, the previous approach is the previous adaptive gradient method only achieve the coordinates rate at 1 divided by square root n, but this paper can achieve 1 divided by n to the power of 2 divided by 3. So with that means the SAGD with Laplace mechanism achieves a sharper bound compared to the analysis. And again, remember the upper bound of iteration t, right? Because like in order to enforce this conditional error, we need to have the limitation restriction for the private space, and we can solve this equation. We can get the upper bound for the iteration number, and so under this iteration number, we can we can say that it maintains the this kind of convergence rate. But so in order to relax this upper bound, and they propose a second method called AGD with sparse vector technique. And the difference, the difference is in this part. So we can that they first split the training data into two parallel two, and in the step they compute the back gradient over these two data set, and then they have a new option here. This from 7 to 10 here. This 7 is trying to to show that's the difference between these two gradients are larger enough or not. If it's large enough, then we will release the gradient with the gradient over S1 and at a different price noise. Now, otherwise we will directly use the gradient from the S2 and then followed by the optimal method here. And under this kind of this is the choice, right? And this is this is called this operation, this validation. They call validation here. And they prove that the SAGD with this sparse vector technique is epsilon delta differential property, and the difference between the second method with the first method is the CS here. The first method there is the T, and here is CS. The CS means the number of times the validation fails. That means this the condition is true over the T number of iterations, and since the worst case, CS will go to T. Most of the cases, if CS will smaller than T, that means this initial private call is much smaller than the previous, and that we can which means we have improved upper bound for T, and if the CS equals to the square root of T, and the upper bound can be improved from the square n the power of 2 to n the power of 4. And by the way, this method achieves the same convergence generalization rate with the first one. Only the difference is the upper bound for the total number iteration. So for the large scale deep machine learning, they derive a mini batch AGD, and the difference in line 3 and line 6, and the train set is partition into B batches with M samples in each batch, and at the iteration number of T, algorithm 3 using can call the previous the Laplace mechanism or the sparse vector machine sparse vector technique to compute the probability gradient on each batch, and followed by some more optimization steps here. And here, this part is we show the convergence rate of the mini batch algorithms, and this part, the first term is related to the initial model, the distance of our initial model to the optimal model, and this part is the rest of the term related to the related to some statistical error, and we can see that this it achieves a rate of 1 over n to the power of 1 divided by 3. And when m equals to 1, if m equals to square root n, and this currency rate can achieve like a 1 over square root n. And when m equal to n, that means like it's full batch, right? You can recover the full batch currency rate, like a 1 divided by n to the to a power or 2 divided by 3. So that like the mini batch shd has like advantage of decrease the computation complexity, but it like exhibit a slower currency rate than SADD. Here is the experiment setting. Like they evaluated they consider they only evaluated the mini batch SJD over several deep learning models on against the population optimization method. And they consider several tasks like classification task, MNIST CFAR, and the language model task, Pentry Bank. They consider different networks, feed forward, deep CNN, and the recurrent neural network. And in order to better understand the generalization ability for each optimization method, with the increasing of the training sample set, and for each task, like MNIST and C10, they construct they build like a multi-trained set with deep sizes, random sample data sets like the original data, 50, 100 or something, and for the CFA10 they choose different training CSN. And this is a result here. This a result like a test loss, and test accuracy for MNIST with a residue activation function. And this part is testing loss and test accuracy of ResNet over CFA10. And you see the x-axis here is the number of samples. And the number increases. The number of data sample increases, training loss decrease, and the testing loss decrease, and testing accuracy increases. And the proper method is SAGD here. So this is red. You can see the proper is show the best test accuracy and test loss almost among all other methods. And then they train this is an experiment over like the language set. They train they include like the perplexity, the test perplexity as access here. The perplex is performance measurement for language model, and the smaller means better. And here, this is our the 2-layer LSTM and 3-layer STM train and train test for this. We see that like for the training perplexity method, mass POP here is better than SAGD, right? But for the data, the method is much better than all other methods. So so this is a conclusion. So this paper focused on the generalization ability of adaptive gradient method, and they propose SADD algorithms try to boost the generalization performance in both theory and practice through the use of different property. And their experiment shows the proposed methods are competitive and often better than the baseline algorithms. Okay. Any question?